All right, so I want to just re-record the wave optics lectures that we've done. They were kind of a little broken up and maybe a little scuffed at times. That's my own fault. But real quickly, we'll just go through these, and hopefully, for those of you that find the review helpful, this will be a good review for you guys as well. So, what is a wave? A wave is an oscillation, at least as the way I think of it, is just an oscillation. So whether you have an object moving back and forth, when I move my phone up and down, that's an oscillation. When I have my phone moving in a circle, that's an oscillation. A string vibrates from being plucked, or even a water wave traveling. You can all model these things in physics with waves. The key thing is periodicity. In fact, for those of you who are familiar with Fourier analysis, even things that don't appear to be periodic can be mathematically represented as periodic things. So really, the fact of the matter is, waves are everything in physics, and understanding the mathematical intricacies of waves is the key to unlocking so much physics. Of course, we won't be going into the math here, but that still stands. So some oscillations don't look like sine and cosine waves. Like when you stretch a string back and forth, that's not doesn't look like a sine or cosine wave. But we can model what's going on in the spring with a sine and cosine wave because sine and cosine waves go up and down. That's how they behave. They oscillate. And so they're very useful as a generalized representation of waves in a universal sense. And that's what I'm saying here. In the same way that the math of mirrors and lenses is the same for most optical systems, the math of waves is universal to all of physics. That's our big partial differential equation of the wave equation, which is one of the most equations in all of, sorry, one of the most important equations in all of physics, I'd say. So to be 1,000,000% clear, or unfortunately only 100 or 100,000% clear here, but I'm 10 times more clear than that. A wave is a mathematical model. Oftentimes it's hard to like actually point to what's moving back and forth. In EM waves, you do have, electric fields are oscillating, magnetic fields are oscillating, but in general, sines and cosines, for example, the electron as a wave, although you can make arguments that there's underlying fields that are oscillating and whatever, the fact remains that the wave representation of it is kind of still a little abstract. It's hard to wrap your head around. That's because it's a mathematical model. It's a perfect model, so to say, because it actually describes what is happening. But the wave itself might be abstract with still physical manifestations. And we represent waves with sines and cosines because of Euler's identity. I'm not going to get into this. It's a whole can of worms, but this is my favorite equation ever. It's beautiful the implications it has, and there's our fan favorite three blue one brown videos about it that explain it brilliantly. So all waves have some important characteristics. They move at a certain speed. They have frequencies, wavelengths, and amplitudes, and the relationships between those frequencies, wavelengths, and amplitudes depends on the wave situation you're looking at. What's really moving in a wave, though? So once again, this does it's a maybe you can call it context dependent, but the key thing I want to emphasize is that this is going up and down. Every point on this wave is going up and down. When we see like the pattern of oscillation of sines and cosines, that looks like you have something moving this way along this wave. That's just kind of like a what's it called? An illusion, so to say. To be 100% clear, is this that's moving in the wave. And there's a pattern to how that moves, which is the wave as a whole, is that pattern. But fundamentally, what's moving along the wave is this. It's just things at each point in space along the wave that are oscillating up and down, like right here, here. Okay. So we have this PhET simulation that demonstrates that kind of nicely, I think. So please don't do that. So if I just move this up and down, I'm gonna create some waves, right? And just focus on like one of the green dots. Notice how the green dot is moving only up and down. If I do the auto playing feature and I lower the frequency a lot just to see, and I draw a line for this right here, you can see this green dot is staying along that line. It's moving up and down, but we see actual wave behavior in the thing as a whole, right? If I up the frequency a little, you can see it looks like a sine wave that's oscillating back and forth. So it's still individual things going up and down, but the wave itself has an apparent sinusoid or sine or cosine shape. There's a lot of other features in this math simulation that you can mess around with. This is more wave physics in general that we're not really going to talk about because we're focused on electromagnetic waves. And also there's some math. That's the wrong one. So real quickly, I want to talk about frequency and wave number. Generally, in like an introductory situation like this, you wouldn't talk about wave number, but I think there's an interesting insight to be had. So this is a YouTube video by well, I get to watch an ad. But it's a YouTube video from the physics class, right? You can see all their details right here. Really good channel that has a lot of good animations like this one. And um, what I want to show right here is the fact that frequency is the number of cycles we have per unit time. So the wave frequency is not the same as wave speed. If I go back to this simulation, I increase the frequency, you can see the speed at which the oscillations seem to be like traveling from left to right is kind of um it might look like it's dependent on the frequency, but to be clear, it is not. In general, wave frequency is not the same as wave velocity. They have a relationship that we'll discuss later, but they're not the same thing. Um, and the frequency is, as he says right here, the number of cycles you have per unit time. Then he talks about period later, which is the amount of time to complete one full vibrational cycle. So if we focus on our green dot right here, and we're interested in the amount of time it takes to go from right here back to right there. That's one vibrational cycle for this wave. So it's like, let's see, 1,002. It's like 1.25 seconds maybe. If I increase the frequency a lot, you can see I mean, it's hard to look out that green dot, but if you just follow it, it's much faster. So a much higher frequency gave us a much slower, or sorry, a much higher frequency gives us a much faster period. And the relationship between frequency and period is that frequency is just the reciprocal of period, and period is the reciprocal of frequency, which would make sense, right? If I greatly increase the frequency, I greatly decrease the period of oscillation, right? So, and when I say decrease period, I mean the period is faster. It's a shorter amount of time. A period is a unit of time. A frequency is a measure of, it's in hertz. It's the number of things per second. Was written in 1/2 which is hertz. So this video as a whole is very good. I included it because in the lecture we watched all of it, but here we're not going to watch it because I'm not just going to steal content from this guy. You can go watch this video. So the distance between two oscillations on a wave is the wavelength. And now this is not a property of a single guy oscillating on this wave. I put it in slow motion. It's not a property of the single green dot going back and forth. It's going to be a property of the distance between two of these peaks or two of these troughs. Crests and troughs is what we call them. So this is a property of the actual full wave object itself, of the illusion that we see. So this is another really helpful animation that's in the slides if you want to watch them. But wavelength is like spatial period. It's like literally the amount of meters between two crests and two troughs. Okay? And there's similarly a spatial frequency, 1 over the wavelength, which is the wave number, which equivalently represents which is the same. So period is to frequency as wavelength is to wave number. It's sort of the number of wavelengths per unit length, right? And so I mentioned this because if you actually look at the mathematical description of waves in physics, you'll see that letter K. And it's kind of confusing what that letter K actually means. But thinking about it like a spatial frequency, I find very helpful for interpreting that. So wavelength and frequency are related by this below formula. Uh, so waves in reality are described by a partial differential equation that we're not going to get into. This is a result of that, as are most of the things we're going to say here. But fundamentally, velocity is distance over time. We know this, right? So the distance covered by a wave is its wavelength, and the time taken by the wave is the time taken by the wave. And so the wavelength, which is our spatial period, divided by our time period, as in the amount of space we cover divided by the amount of time it took to cover that space, is lambda wavelength divided by t period, which is the same as f times lambda. Okay. So this is our mini derivation of this equation right here, which is going to be a very important relationship that we use very often for waves. Does a higher wavelength always mean a higher frequency? And what relationship is the below insufficient? So there's situations in which changing the wavelength, excuse me. So when we have an effect called dispersion, which in general in physics refers to mediums where there is a frequency dependent wave velocity, this relationship is insufficient. We can't just make this blanket statement that this is true because our wave might be some composite wave with a bunch of different components. And so it's important to remember that the wavelength when you, excuse me, sorry. So if you think about how refraction works and how what frequency and refraction really are, frequency is a property of the wave of the source of the light itself. It's not really a property of the wave. It is a property of the wave, but it's more a property of the source. Whereas the wavelength is a property of the wave that most relevantly changes when you change media. And you think about how refraction works and how it impacts the angles at which waves go and the speed of waves, that should make sense. So to be clear, what I'm saying is if a wave changes medium, its wavelength will change, but its frequency will remain constant for a light wave. This is, yeah. So wavelength and frequency are intrinsically related because one gives spatial period and the other gives time period. They're explaining the relationship between space and time for a wave because waves travel in both space and time. They're oscillating in time, but they might be moving in space, as our electromagnetic waves do. So, yeah. And when a wave refracts, does the frequency change or does the wavelength, what I just said, the wavelength changes, but not the frequency. Let's talk about electromagnetic waves. In the same way that F equals ma is our big equation for classical mechanics, electromagnetic waves are described by Maxwell's equations. Not going to get into them, but everything we talk about with electromagnetic waves comes from a very surprisingly, I mean, they look complicated, but they're actually somewhat simple if you abstract past the calculus set of four equations, which I think is it's pretty cool actually. We can do so much for just these four guys. The two foundational relations that we're going to use for electromagnetic waves, which require a bit of some stuff that we're not going to get into, are the below. This is just the equation we showed on the previous slide. Wave velocity equals wavelength times frequency. This is the speed of light c, which is going to be 3 times 10 to the 8th meters per second. And this is the energy of our wave, which equals Planck's constant, 6.626 times 10 to the negative 30, 10 to the negative 34 joules, uh, uh, joules seconds. And that gives us the energy of our wave in joules. So these are two very useful relationships for electromagnetic waves that we're not gonna really further discuss or get into, especially this last one. But that one's very interesting because it gets into the quantization of electromagnetic waves, which is Cool. So what's actually vibrating in an electromagnetic wave? It's a wave, so there's an oscillation underlying it. It's produced by a thing that's moving back and forth. Electromagnetic waves are produced by accelerating and charged particles. But what's actually oscillating is the electric and magnetic field components of our wave. So an electromagnetic wave is made of two components. You have a electric wave component, which remember there's just individual like points that are going back and forth. So this electric field right here, which is basically like a force field. If you think about how gravity acts on us on Earth, gravity is not like literally puts like gravity doesn't have hands that it's holding me to the Earth. If I jump up and I'm not even touching the Earth, gravity still acts on me because I'm in a gravitational field. It's a invisible kind of thing. I mean, it's not really invisible as a field, but invisible in the sense that we can't see it. It's not in the sense that it doesn't exist. The point is, uh, of the field is what holds us to this, a gravitational field. It's not like a literal set of hands that's holding me down. The same way that an electric field acts on charged particles to move them around or provide force on them. You also have a magnetic field component, which is perpendicular. So imagine this blue wave as coming out of and into your screen. Okay. So the magnetic field is oscillating perpendicular to the electric field component. And magnetic fields are going to act on I mean you can think of magnetic fields as a magnet. I mean that's really the best way I can explain that briefly. So what's important about this is based on the direction of those two components, we can also get the direction of travel of the wave. It's mathematically given by the cross product, but really it's given by the only direction that the electric and magnetic fields are not oscillating in. So here it's going to be this way, okay? Because that's perpendicular to this guy, perpendicular to this guy. And do that a little better. Perpendicular to this guy, and these guys are also perpendicular, okay? So they're all perpendicular to each other. So the wave itself represents the strength of that field at each point in time. And this is just a helpful animation that shows that. So, of course, I have to watch an ad for Lysol. But this animation shows that by Patrick Vanikoff. So you can see this blue component is our electric field, it's the opposite of what I drew. And you can see it's perpendicular to our red component, to the magnetic field. And it's moving in space, right? So you can see, although this wave looks like it's moving, remember, it's these individual field lines that are changing. The strength at that point in space of the force from an electric field is changing over time. And you can see that's our wavelength goes from this point right here to that point right there, which is the same as our crest to crest, or trough to trough. And our amplitude is literally just like the height, so to say, of our wave. And that amplitude corresponds to the intensity of our wave. The amplitude is going to be actually the strength of the light that we see, the intensity that we see. So let's talk about the physically important properties of electromagnetic waves. The frequency of an electromagnetic wave determines the color that we see, okay? So different frequencies and wavelength are assigned to different parts of the electromagnetic spectrum. Does red or blue light carry more energy? Quickly think about that for yourself. So blue light is more energetic than red light because it has a higher frequency than red light, and E equals HF, as we showed earlier. You can also see as we greatly increase the frequency, our wavelength is getting much, much smaller. It's getting much more narrow. And I mean, you can kind of think of this like, oh, they're much more compact, right? Our smaller wavelength is forcing many more waves per unit time, which is sort of carrying more energy. That's not really uh, a physically sound way to think about it, but that's a good way to remember it, I'd say. So just one thing to abstract away from what we've talked about. waves are used to model things, right? Often they're not going to be physical themselves, but they'll have physical effects. We can't touch an electromagnetic wave. We can't physically, grab it and measure these properties that we're talking about. But these properties are very real. And so we can model electromagnetic waves and see, okay, we know all these properties of this wave are true. We can sort of measure all these properties based on their physical effects. And as a result, we know this model is correct. It's similar to how I can model with you can modeling in general. Sorry, let me rephrase. Modeling in general, you usually think of it like you're you see some data and you want to fit a line to it, do a linear regression and find a line of best fit. But modeling in general is just fitting any framework from any discipline to describe what we see, what effects we're seeing in the real world, to rationalize those effects. And electromagnetic waves do that as a sort of perfect kind of model. So these are the few problems. We'll work through them. Then these are the answers for those problems. So now I'm just going to go through the next set of slides. We start with a review of what we just talked about, which I think will be helpful. So waves are oscillations, and they have properties like wavelength, amplitude, and frequency. So just to recap, wavelength is going to be the distance from here to here, or from here to here, or from here to here. They're all the same. Frequency is going to be the number of oscillations per unit time. And amplitude is going to be the height of that wave. That's going to correspond to the intensity of our wave. Frequency and wavelength are related by the velocity of a wave. That relationship is going to be V equals F lambda. And when a wave changes media, its velocity changes. Wavelength and frequency are both changes. The answer is the wavelength changes, okay? Electromagnetic waves are the waves responsible for light specifically, and they have electric and magnetic field components that are perpendicular to each other and oscillate through space and time. And they travel in the direction that's perpendicular to both the electric and magnetic field components. And those properties of EM waves have physical meaning. The energy of an EM wave comes from its frequency. Color comes from its frequency, from its wavelength. So and then we group those frequencies and wavelengths into different classifications. We have our radio waves, our microwave waves, and it all depends on roughly where the wavelength is. And that's useful because different types of uh, electromagnetic radiation have different properties and ways that we use them. So now we're going to talk just a little qualitatively about interference, diffraction, and polarization. So when we add two sine waves or combinations of sine waves, we get just literally the combination of them, right? And that's what we're showing here, right? So if I draw a sine wave in red like this, and I draw another sine wave in orange, that's like a little smaller than that, but has the same frequency and wavelength, then the resulting wave, which I'm going to draw in dark green, is just the sum of those two guys, right? I can't draw, but you get the gist. That last bit's wrong. So that's what's going on here. We're taking one wave, we're adding it to a second wave, and we get the resultant wave. This is just literally because mathematically we're adding to it's 5 plus 3 equals 8. Sine plus another sine equals sine plus another sine. We're just adding two things here. There's nothing special going on here. What is special is that as the math predicts, the waves do that. Our model of waves as sines and cosines is, it's correct, obviously, because that's what they are. And so when they interfere with each other, when two waves enter the same region in space, they're going to add or subtract from each other. That's called interference. So constructive interference on the left is going to be when their crests and troughs line up to create a much larger resultant wave. Destructive is going to be when the crests line up with the troughs and the troughs line up with the crests, so the wrong way, to give us destructive interference, no resultant wave. I generally refer to constructive as any time they're adding together at all, and destructive as any time that they're subtracting from each other at all. But some people just say it's like constructive is the max amount of adding together, destructive is the max amount of taking away from each other. The point is, waves interfere to give different resultant waves that we actually observe. We're not going to observe each of these individual components. We're going to observe the resultant wave when they occupy the same area of space or the same mathematical whatever. So briefly taking a break from that interference stuff, when a wave passes through a small slit, we create many new waves coming out of that slit, which is kind of a poor way of saying that we create these circular wave fronts. Okay, so you can think of each of these things as like we have our wave here, our wave here, here, same thing here. These are all like little wave guides that are traveling like this. And they all are kind of in the same area. They have the same constructive, same peaks, same troughs, and like that. When we go through the slit, it's gonna kind of pinch our waves to look like this. So now they are the same in the sense that if we look like radially along a circle, they do look the same. But if you take just a slice, you'll notice that some of them are at their peaks while some of them are at their bottoms. And so that's what we observe in single slit diffraction. What's really going on is this wave is basically like interfering with itself. But if I do some light and just let it pulse a little, see, this is what's going on. But then when it enters a single slit, it pulses or it pinches itself. And on the far right of here, these red spots that I'm going to circle are where we're having destructive interference observed, okay? But then these green spots, I'll just not use all these orange, or we're going to have our constructive interference observed. And that's just because when you go through a slit that's smaller than your wavelength, you're going to sort of have um, it's going to pinch your wave. And you have similarly interesting effects with double slits, right? The excuse me, the double slit is when we take a second slit and we add two slits here, and we do the same thing. Not only are we going to have these single slit effects of the waves creating circular wavefronts, but those circular wavefronts are also going to interfere with each other. And so we're going to have more interesting spots of darkness, like right here, 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 but then spots of extra brightness, like right here, here. So it's very there's some very good mathematical descriptions of how this works that are actually not that complicated to describe. They require a bit of, math and a bit of sine and cosine and trig and even a bit of calculus to work through, but ultimately they could be much more complicated for how interesting the phenomena they describe are. What's important to remember is that, I forgot to mention this on the previous slide, what we observe in our double slit on the left, that deep red wave, is going to be a combination of our interference effects and our diffraction effects. Both of them are contributing here. So, and the most useful optical phenomena, sorry, I would call them some of the most useful optical phenomena because they can be used for interferometers, which you can use to make measurements of like really small things like the wavelength of a wave, which could be on the scale of like nanometers, without actually having a ruler that's like on the scale of nanometers. So this right here is our Michelson interferometer. It's kind of our most basic interferometer. And the way this works is we can take some light, put it into this thing right here, which is our beam splitter, and it sends one beam going towards this mirror and another beam going towards this mirror at the top. This mirror is fixed, okay? This is a fixed reference mirror. So the length of this beam right here is going to be constant. However, this mirror right here, we can move around. So this can be moved around. And so we're essentially changing the distance each wave has to travel. If we have a wave that looks like this, it'll reflect like this, and it'll go here. But I can change the amount or where this wave is in its path to then see the wave that enters its detector change the interference there. And the way these two waves interfere, coming from the measurement mirror right here and the reference mirror up here, depends on the amount I've moved the measurement mirror and the wavelength of the wave. And there's a direct relationship between the two, which means, and most crucially, we don't need to move the measurement mirror like 1 nanometer to get 1 nanometer of difference on this wave right here. We can, as long as we can very precisely move the measurement mirror, we can do very good calculations to see, okay, this is the wavelength of our wave because I saw interference constructively at this measurement mirror distance, but destructively at this measurement mirror distance. So interferometers are very, very cool devices, and there's a lot of them out there, Fabry Pro, Mach Sender, a lot of cool ones that you can look into. Now we're going to talk about polarization. So the electric and magnetic components, as you said earlier, of an electromagnetic wave are always perpendicular. And polarization is defined as the direction in which the electric component of that field oscillates. The blue right here is our electric component, and our polarization is the direction that blue oscillates. You can think of polarization like literally when you go up and down on a rope, you're going to be oscillating up and down. And the direction that you're moving your hand to oscillate that rope is the polarization of the wave. These black things right here are polarizing filters. So this filter right here is going to be vertically polarizing. And when we vertically move our hand to vertically polarize a wave, it passes through. But if we horizontally polarize our wave and we're using a vertical polarizer, we can't get it through. It's not going to let us. It's going to stop all that movement. This is to say that polarization is essentially a way of filtering waves. And because that's not how it's defined, but that's what it can be used for. Because sunlight and just light sources in general produce unpolarized light, which can be thought of as light polarized in like all directions. And so this light can be polarized, and the idea of polarization and similarly spin have similar ramifications when it comes to polarizing and collapsing, which we'll discuss when we talk about the Sturger-Luck experiment. But when we repolarize light, we lose some of the power because we're basically getting rid of like 50% of this wave, right? You think about this component right here, we're getting rid of all of this, you know, please. We're getting rid of all of this horizontal. So this horizontal guy right here is just, it's gone now, right? This diagonal guy, we're going to take about 50% of that guy. And this vertical guy, we're going to take all of that guy. So there's a continuum. There's waves that are like closer to horizontal, we're going to maybe like 20% or so. Waves that are close to vertical, we're going to get maybe like 90% or so. The relationship actually depends on the cosine squared of the angle between our polarization, I equals cosine squared theta times I naught. That's our Malice's law, so relationship, which is not terribly difficult to derive. And the reason this is useful is because if we have some light, we polarize our light to get it all vertical, then we take something that does something to our light, and it polarizes our light to a new angle. Then we analyze it and see, okay, well, now we have this much power. We found out that this optically active thing polarized our light by an angle of theta. What does this tell us about our thing? So polarization is very useful in that sense. It's also useful, and this is like slightly relevant, I'd say, because of Brewster's angle. So reflection, due to some deeper physics, Maxwell's equations, of course, which are due to different things themselves. Reflection acts differently on different types of polarizations. So if you imagine the situation that I'm drawing here, if you look at my video, it's easy to see. Actually, if I stop my screen share, it's actually easier to see what's going on. So if we have, this is a reflecting surface, and we're going to send a wave into it. But our wave may be composed of, it may be composed of light that has polarizations that are, within the plane of incidence for our light, like this notebook right here, but also perpendicular to that plane of incidence, okay? And so when you look at these diagrams right here, when we talk about S and P polarized light, it's sometimes hard for me at least to remember the directions and figure out like exactly what's going on. But our unpolarized light, we think about plane polarized light, which is going to be in the plane that our light is moving. Okay, so this is where it refracts. This red is going to be the plane. Okay, the light's moving along that plane. All the polarizing directions within this plane are called p polarized, and anything perpendicular to this plane is s polarized. And because of, I mean, the fact that this is like, I guess, linear algebra dictates that fully describes all the polarizations we could possibly have. So at Brewster's angle, which is going to be this angle right here, we have a couple of interesting things happen. Our unpolarized light goes into the refracting situation and out reflects completely s-polarized light. These green dots are completely s-polarized light. Now, our reflected wave will have mostly p-polarized light, but it's not going to be completely p-polarized light. It kind of depends on some more, it depends on the index of refraction relationship. But most interestingly, the angle between our refracted and reflected beams is going to be 90 degrees. So when the angle between these beams is 90 degrees, the reflected beam is completely s-polarized. So that's the really key observation here. You might be surprised to see there's both refraction and reflection going on. But I mean, if you think in general, if I look at like this glass this glass of water, there's some light that's going to be reflected at me. I can kind of see my own reflection in there, but there's also light that's being refracted. Reflection and refraction happen in all. The portion of reflection and refraction depends on the Fresnel coefficients, which depend on other things themselves, which we're not going to talk about just because they're kind of mathematically gnarly. Although I do include them right here. And as you can see, mathematically gnarly, we're not going to discuss them. But I mean, they're very, very useful. So that's all we got for this. This is our discussion of electromagnetic waves. That's where we're gonna conclude it. Hopefully this is a good review for you guys. And yeah.